to record.
Okay, it's recording.
Alright, so, again, final exam. 7 problems, 3 that are numerical, 4 that are short answer. So, from the top. First problem is on optics.
So it's numerical?
Isn't this just like the
Yeah. Alright? You have 2 choices when you're doing this optics problem. You can either go down the route and do mirrors, or you can go down a route and do lenses. Okay?
Does me only have to study one, or should we know both?
Well, the question is, if you look at the lens question, you're like, oh dear God, I don't want to touch that with a 10-foot pole, then you're going to wish you had studied mirrors. And if you look at the mirrors question, you're like, oh my goodness, what horrible abomination is this? What hath man wrought in his, hubris? You're going to want to wish you had studied lenses.
Okay.
So I would recommend doing both. What?
So there's no drawing for this. We're gonna walk
There is
away.
drawing.
Oh.
There is the whole kit and caboodle. So, common to both of these things, we've got kind of this one overarching equation that just keeps coming up again and again and again and again.
Yes, we do.
It's our thin lens equation, it's our spherical mirror equation. We have a focal length to define these things when they're spherical, either lenses or mirrors. We have an object distance, which is coincidentally the distance to the object, as measured from the center of the lens or from the farthest point on the mirror, the image distance. We also have the magnification, which we can define in terms of the distances or in terms of the size of the object, the size of the image. So these are common to both. Yes, Sam?
On like the test, on the final, are the equations just going to be like in a big long list? Not
Yeah, there is a
organized
giant
at all?
page of equations at the end. It is, I just literally copied and pasted the equation sheet from every test into it.
Oh,
What is
So
the
will they be in like the order of the units or something?
Ish.
Okay. Yeah.
Alright. The other thing that is common to both of these are ray diagrams.
oh, my enemy.
So, what makes mirrors special? What do mirrors do?
Reflect.
Mirrors reflect. So we've got light bouncing off of things. So, what kind of mirror is this?
Convex.
Concave.
Or if the object is, I guess,
Concave.
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 this is a concave mirror, if this is our object. If my object is instead on this side,
The person is the object. Convex.
then it is a convex mirror.
So,
All
wait,
right?
do you still have those videos on the
Every video that,
haiku,
yeah, I've not taken anything down from haiku. When we're drawing our rays, what do we have to do? What point do I have to kind of put on this picture to make it complete? I have to put a focal point somewhere. Focal point, yeah. When you're dealing with lenses, remember the focal point is told to you. When you're dealing with mirrors, spherical mirrors in particular, how do we know what the focal point is?
Image radius.
The focal length is half the radius. Useful trivia.
Do we need to know that?
For circular, what?
It's probably going to trivia on the equation sheet. For spherical mirrors. Usually I'll just tell you the focal length. On some of the homeworks you need to do. Remember, general rules for ray diagrams: in parallel, out through F, in through F, out parallel. Those are the rules in general. It always comes to those 2 things: in parallel, out through F, in through F, out parallel.
It's always like that
It's always like that
for all mirrors.
for all mirrors. Sometimes it's a little tricky. So like if it's on this side, it goes in parallel, and it can't go out through F because F is on this side, so it goes out from F. In this case, it aims for F but doesn't really get there, so it bounces at the mirror. But the idea is always pairing a ray that is aiming kind of either to F or from F with a ray that's parallel to the principal axis, and a ray that's parallel to the principal axis and then is going out either to F or from F. So it's always parallel and F, parallel and F, F and F. Always that's the pairing.
Wait,
So-
out parallel. Sorry, I'm talking
Again.
myself.
There are examples. So there are sketches for all of these on the homework from this unit. And remember, you can bring your table with you. So if you look on Haiku, there are all of the homework has written out solutions. So that has sketches for every mirror combination
I actually did.
and every lens combination.
2 tables, right?
2 tables, one for lenses, one for mirrors. Now with lenses, what do lenses do? They refract, or in kind of more common English, bend light. Which means that light passes through a lens. What kind of lens is this?
Converging.
This is a converging lens. When rays of light go through a converging lens, what do?
Come together.
They converge, they come together, just like the Beatles song.
Come together. Okay.
Anyway,
Let's all start
Go
thinking
on
about
video, you know.
so. You say that as though that's the most embarrassing thing I've ever been caught doing on camera.
Yeah, there was that weird skipping thing that one time with like.
Oh
Okay.
yeah.
Oh, that was funny. We could just
When-
like.
No idea.
Okay. Back to physics. And we're zooming.
I'm pretty
on
sure
the
that-
What kind of lens is this?
Diverging.
A diverging lens. What happens to light as it goes through a diverging lens?
It diverges.
It diverges. Shockingly enough, these are named appropriately.
Sadly, yes.
One thing that you might notice, so the way that I've drawn these, I should indicate what direction this is. The bending happens at the center of the lens because we've made the tacit assumption that these are all thin lenses. So the actual shape and dimension of it doesn't matter because we made the assumption that it's just converging or diverging with no other criteria. Technically, the shape, size, and material is what goes into determining the focal length, but we just said thin lens with a focal length, done. So, like how bent this is, if it's spherical, if it's elliptical, if it's flat, if it's curvy, no interest to us. Now, here's one thing that could be very interesting. What if I had multiple lenses? Or, for that matter, multiple mirrors. So what if I had a diverging lens, or I'm sorry, a converging lens, and then a diverging lens?
Have we done this before?
Glasses.
Rachel, resist the temptation.
Your eye is a converging lens. Glasses can be converging or diverging lenses depending if you're nearsighted or farsighted, as we talked about in class. How do you think you would address a problem like this?
Would you do the diverging and then the converging?
Well, let's say my object is over here.
Hey Amanda, is there any chance I could sit in that chair because my back is hurting? Okay, cool. My apologies to the camera watchers.
Okie dokie, artichoke.
Much better.
Hi, I'm an object.
Doesn't mean you should objectify it, though.
Ha 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 ha.
I've been saving that up for a while.
And it wasn't even that
But if he came up with it on its own,
Failed
it's.
the physics
Ah!
And now this is an official physics video because we've got Sam on camera making a face.
funny. No, I
Yes?
think it wasn't as funny as
Oh, sorry.
the artichoke.
No, actually, I think that because you're better.
Yep, that works.
Guess you just passed the physics project. Alright, so if there were just the converging lens, what would happen?
It would converge.
Yeah, so I'd be able to say, you know, alright. Let's say the focal length is really close. Maybe. Or no. Yeah, really close. Close is good.
Is there a video on lenses?
Yes.
Oh, I meant mirrors. I meant.
Alright. So
Oh, so that's
Oh my god, it looks like that person's being killed.
More like suspended by their feet and then having their head laid down on a plank. And Okay.
I was thinking like laser.
What does that say? Hi,
Oh yeah, there is a laser going through its head.
What?
An image.
Wait, why does that?
I think it's just trapped in a box that is the length of its body, so it like.
That's the principal axis. So his
So
feet
where's
stay
the
on the
focal
axis.
thing? Where's the focal thingy off in that picture?
The what?
Oh, this is gonna be focal thing.
So here's our focal points, apparently.
I'm just like the higher amount.
Wait, what's the? Oh, I get it. Never mind.
I mean, this should say hi, I'm an image, and it should be backwards and upside down. At least upside down.
Incorrect. Okay.
We're going a little meta with this. So if I just had one lens, this is what I would be, right? So now what does the second lens see?
It sees the image.
Yeah. The image of the first lens is the object of the second lens.
So how would we draw that, Mr. O?
So you would just keep going like a normal diverging line?
Yeah, so then I would ignore all of this stuff, and this would have two focal points. So I'd go in and out, and I would go.
Wait, what are you doing?
I'm treating this image like it were the object.
Oh, for that. Okay. Oh. Well, I can't really see that.
Wait, where's F again? I can't really see.
Wait, you should.
Man, he must feel so used.
What's the name
So
of the
F
part where
is- Those two
Oh,
dots.
I made this backwards.
I had to look at the.
Yeah, it's kind of upside down.
So.
But basically, this was the object for my diverging lens, and this was the image of that object. So this is the image of the image of the object. All right.
One,
So you
two.
go in parallel and then you go.
Is the one that going in through
Up?
the focal point is going in through the
So this
second
one,
focal
it goes for a diverging. Remember, it goes in through the far focal
Yeah,
point
okay.
and out parallel. In parallel, out from the near focal point. As opposed to this goes in parallel, out through the far, in through the near, out parallel. It
And then
switches.
you go backwards.
Yeah, because these two don't intersect.
Okay. So
I
then,
have to extend.
So then my person can be on the same line. It's still on the same line. And
Yeah, his feet still stay on the axis.
and
Wait,
he's
can you
upside down?
Draw
Inside.
again,
Yes.
but like regular size. Up. Because it just looks like a jumble of bread.
So if this is the general thing for a diverging lens, all right.
So he's really small upside down.
Here's my person.
I can't even see the person.
Here are my focal points. And this goes in parallel, out from F, and then into F, out parallel.
Into the far.
That's not right. So here
Oh, okay.
is my image. All right.
How would we do that for a mirror?
Well, for a mirror, it'd be the same thing. The reflected image would be the object for the next mirror.
Can we do one of those?
So you might put one like this on the test.
I mean, given that I mentioned this during the review session and
Yeah.
we've never really discussed it in any depth or interest before, this might be perhaps a leading example.
Which is why can we do one for the mirrors too?
I leave it to your creativity.
But I just don't.
We've got 6 other problems.
It's the exact same thing.
It's the exact same idea, but
But
with,
where would the other mirror be located?
it depends on how you set it up. My recommendation, what's the most common example you can think of where you have 2 mirrors?
Those dressing rooms.
When you're in a bathroom that has 2 mirrors.
Yeah, you get like those infinite halls of reflection things. I would think about one of those.
When you're in a restaurant, there's mirrors in front and behind you.
I hate watching myself eat.
Question 2 we
weird.
said was on circuits.
Oh yes.
All right.
Circuits.
For circuits, we are focusing in on kind of, yeah, a couple of different aspects of this. So here is a circuit, yes?
Yeah.
I have 3 resistors, R1, R2, and R3. One of our claims was that this could be reduced to an equivalent circuit or an effective circuit.
Is this one of the number ones?
Yes.
Wait, an equivalent circuit?
Where the equivalent circuit was just one resistor,
Oh, one resistor.
this REQ. So, how does this happen? What can you tell me about these resistors and how can I smush them down into one lowly resistor?
Wait, wasn't parallel the one where, that's a parallel one, right?
Which things are parallel?
R1 and R2.
R1 and R2 are in parallel. Yes. How do we know they are in parallel?
They're parallel. Like they go like this. Like there's no thing.
The electron.
No,
There
there
is
is.
no-
There is.
yeah.
There is.
So when we're thinking about this parallel, we're thinking of as OR. We go through R1 or R2. What's the other option?
And
Series. And. Is anything in series in this circuit?
R3.
Is in series with
No.
what?
R1 and R2.
So if I go through R1, do I have to go through R? So if I go through R3, do I have to go through R1?
Yes.
No.
Not really.
Because you could go through R2.
Or R1 is in series with
Is it
R3
where-
and R2 is in series with R3.
So if I go through R2, I'm always going through R3, and if I go through R1, so if I go through R3, I'm always going through R2, and I'm always going through R1?
Not
So
Because that's what it means for it to be in series. If I have, that has to be a strong and.
R1.
Whenever I go through R1, I have to go through R3, and whenever I go through R3, I have to go through R1.
Yes.
No.
Wasn't it that electrons will go through both of them?
Some electrons will. What does one electron do? If I go through R1, if I go through R3, did I definitely go through R1 to get there?
No.
So then we
Either
can't
way,
say that
one or the
R1
other.
is in series with R3. We can say this thing, it has to go through one of these to get there. So that's why this is the next step. These two are definitely in parallel, but neither of them is really in series with R1, with R3,
Separately,
separately.
but together.
But together, will have some R equivalent, we'll say parallel here. And so our new circuit will look like this. All right. How do I find, what is this?
There was an equation.
There was an equation.
Is
Isn't
it
it like adding
R1 plus R2 under 1?
Kind of. So in series, it's nice and easy. It's just R1 plus R2. Does anybody remember what the weird one
It was
was?
like the dividing by like you were dividing by stuff.
Yes.
Let's do the normal one.
Could we do like the normal one first?
Well, unfortunately, we had to do the parallel ones first. So in parallel, this is what we get. One over R equivalent is equal to 1 over R1 plus 1 over R2. We get all these 1 overs. Again, just like in here, there are all these 1 overs. This 1 over is kind of a thing that keeps coming up. You can't get away from fractions in physics.
Then when is it just, is there just one?
We will get there. So in this case, I could solve this, and what I would get, I would have that R equivalent. I have to flip this side, which means I have to flip this side. Let's put this whole thing, this 1 over nonsense, at the bottom of a fraction. So it looks like this weird, crazy fractions inside of fractions.
complex fraction.
Yes, which is much nicer if you have numbers.
So how would
So like, let's say that R1 was 1 and R2 was 2. And this would be 1 over 1 plus 1 over 2, which is 1 plus a half, which is 3 halves. So 1 over 3 halves is 2/3. So if we want to take that case where R1 is 1 ohm, R2 is 2 ohms, then R equivalent parallel, what we called here, this, is 2/3 of an ohm.
Do we still have to add in the third resistor for that equivalent?
Well, so we still want to get to this, right?
Yeah, so we still have to add in the third one, right?
So what can we say about these two? R equivalent parallel, which we said is 2/3 of an ohm, and R3.
Are those a series?
These are definitely in series. If I go through R equivalent parallel, do I have to go through R3?
Yes.
If I go through R3, did I have to go through R equivalent parallel?
Yes.
These are definitely in series.
So wait, what we just did, was that the equation for the
When they're in
for
parallel.
R1 and R2?
Yeah, that got R1 and R2 down to this equivalent resistor. So in series, we know that R equivalent is equal to R1 plus R2. In general. In this case, it would be R equivalent parallel plus R3. Those are the two resistors that are in series.
How did you get 2/3 ohm?
1 plus a half is 3/2. 1 over 3/2 is 2/3.
Okay.
REQ
Alternatively, it counts.
parallel plus. Wait, RE.
So this
So
resistance
it's like
plus
all
this.
of 1, 2 plus 3.
In kind of. In general, it's this. If I've got two resistors in parallel, in series rather. In this case, the two resistors I have in series are R equivalent parallel and R3. So it's R equivalent parallel plus R3. This is just some generic 1 and 2. If I got two resistors in series, some random old R1 and R2. For us though, it's these two. So let's say that R3, being so creative, is equal to, I don't know, 3 ohms. We get a pattern. We'll go with it. What's 3 plus 2/3?
3 2/3.
Or 11
Or,
thirds.
yeah.
So this equals 11/3 ohms. So this is 11/3 ohms. Because now we're down to just that one resistor. This is what we mean when we say reducing a circuit. We're bringing it down to one equivalent circuit. From here, I could ask, what is the current in this circuit? And now there's only one current because there's only one loop. So there's some current in here. Let's say this was a,
Sorry.
Isn't current like Ohm's law?
yes. Let's say this was an 11-volt battery. If such a thing totally exists. What would the current be?
VBAT equals 11.
11 volts.
What's that called? Reduced what?
So this is a reduced circuit, or an equivalent circuit. We say it's reduced to an equivalent circuit. Let's say.
Real V.
So how do I relate voltage, current, and resistance?
Isn't it delta V equals IR?
Ohm's law, delta V equals IR. Do I know what delta V is for this resistor?
Inverses. Joint.
Do I know what R is for this resistor?
Yes.
Can I find out what I is?
Yes.
What's I going to be? It's a very deep question, I know, but
What does this have?
It's
does the delta V have to do with
33
how,
elevenths.
like the loop rule too?
kind of, yes. We're not going to worry about that too much.
Okay.
11 over 1 time.
Or just
33
Is it just
elevenths.
11?
Yeah, 3.
Wait, what's the
Oh,
change in V
equals-
equal to? Is that 11?
Yeah. Because that's kind of this idea of the loop, right? We picked up
Oh,
11
yeah.
volts going around the battery, we lose 11 volts, then in the resistor, and we're back to where we started.
Wouldn't I be 3?
Yeah. Because it's 11 divided by 11/3. 11 over 11 over 3 is 3. 3 what?
Amperes.
Amperes. Unit of current. Alright? This is the kind of stuff that's going to be on the circuits bit of this test. combining resistors, figuring out if resistors are in parallel or in series, and using Ohm's law.
Not the loop.
Okay.
Not the loop rule, not the node rule.
Yeah.
Alright? We okay with this?
Yep.
Goodbye.
Number 3.
Oh my god, there's 7 of these.
No, there's just.
This is the last one with numbers.
Yeah, we have 10 minutes till next period.
Unit conversions. Alright, so then apparently we're going to do the back 4 tomorrow, I guess. What do we remember about unit conversions?
You can put like one thing over like 60 seconds as a minute, and if you want to find how many minutes are hours.
Oh, you put the other thing like if something's on the bottom, you don't cancel it out. It's multiplied by something that has like the other thing on the top.
So one example, how many seconds are in a day? What do we know a day is equal to?
24 hours.
We know that one day
You've only got 46.
is equal to 24 hours. What is 1 hour equal to?
60 minutes.
What is 1 minute equal
Live
to?
like we're dying.
Yeah.
Isn't that by like 2 more hours?
This is the kind of information you would be getting. You would be getting relationships between units. That 1 day is 24 hours, that 1 hour is 60 minutes, that 1 minute is 60 seconds, that 14 conglomerates is equal to 1 heading, that, 16 gobbledygooks is roughly 7 buffets, that, Snarty Bart Blast is equal to 14 Zappa people books. Right? The Slutty Bart Fast is equal to 14 Zappa people books. You check it out of the galaxy reference. Bam.
Otherwise, there's 86,400 seconds.
Well, getting there. So how do we use this information? If I have 1 day, what is the next unit I can convert to?
Hours.
Hours. So, do I want hours? So do I want day on the top or on the bottom?
Bottom.
Bottom. Which means what's on top?
Hours.
Hours. 1 day, 24 hours. This is our conversion factor. We're taking this expression, all right, and saying that, all right, 1 day is 24 hours. Okay? These are the same thing. So this is overall equal to 1.
Is that equal sign?
No, it's a dot.
It's like a multiplication.
What's the next thing we're going to do?
Convert to minutes.
All right, so we're going 2 minutes from what?
60 minutes.
Hours. So hours is going top or bottom?
Bottom.
What's on top?
Minutes.
And what do we know about hours and minutes?
There's 60 minutes to every hour.
60 minutes, 1 hour. Where are we going next?
Seconds.
All right, minutes on top and minutes on the bottom. Seconds on the top, minutes on the bottom. What do we know about these two?
61.
60 seconds is 1 minute.
It's at 61 seconds.
So when we're looking at this, we see that we have day canceling, hours canceling, minutes canceling, leaving us with seconds, assuming we do all of this multiplication. 1 times 24 times 60 times 60 divided by 1 times 1 times 1. Yes.
I did it starting with seconds. Is that okay?
I mean, multiplication is commutative.
And
This is just, I think, a kind of a nice way to see the progression. So if you don't have units you're comfortable working with, this is going 1 step at a time, always to kind of the connecting unit.
yeah, so I did 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day.
Yeah, it's the same thing, because 24 times 60 times 60 is 60 times 60 times 24. Doesn't matter which way you write it down. It's just a question of, if you didn't know what all the steps in the middle were, how would you be able to figure that out? Because we know we're moving from 1 unit to the next unit, and then from this unit to the next unit.
Okay.
All right? But I mean, if you know you're ending in seconds, so you know seconds to minute, then the next connection has to be minutes to something else to the next thing, and the next thing too. All right?
Is it gonna be like, you're not gonna have some weird thing like,
Yeah, he is.
no, like, is it gonna be like common, how
No.
many something is in a something?
It's gonna be like.
It's going to be totally made up stuff.
Gonna be like 5.
And even better, it's going to be made
yeah.
up metric stuff.
No.
Metrics.
So, other common conversions. Remember, we talked a lot about metric prefixes.
This is like 2 counties and a
He's not the answer.
So 1 kilometer is how many meters?
2,864.
What?
Is it 100?
1,000.
1,000.
1,000. Kilo is 1,000. All right. What is the short way to move between metric prefixes?
Step chart.
Move in the decimal. All right.
That was a nice error.
Sometimes I get lucky.
So we're gonna need to know how to do this.
So I will tell you the prefixes you need, but you need to be able to go from, like if I tell you how many millisomethings you have, you need to tell me how many somethings that is. If you have 600 milliseconds, how many seconds is that?
Oh, is that a real question?
So if you have 600 milliseconds, is that many, so is a millisecond many seconds or many parts of a second?
Many parts.
Parts of a second, right? So if I have 600 milliseconds, is that going to be a lot of seconds or few seconds?
Little bit.
Few seconds. Milli, it tells me I have to move how many places? 3. Milli means 1,000. So 600, right? Which, oh god, I can't even. 600. I have to move the decimal 3 times to make it smaller. Once, twice, thrice. Why I have a board literally right in front of me.
Throwing in the air.
Once, twice, thrice.
There you go.
So it is 0.6 seconds. All right. So you gotta be able to do. You gotta remember how to do that kind of conversion also. Maybe a little scientific notation.
No! Oh my god, no. I hate that.
But we didn't go over scientific notation.
Yeah, we did.
Yeah, we did.
Can we go over that now?
So I mean, 1 over 1,000 is 10 to the negative third. And scientific notation is just 10 to the
so
10
we're
to a
just gonna
pound.
have to like do a problem and then just put it back.
I mean, or I might give you one of these ratios with, you know, instead of it being like 7 million, it would be 7 times 10 to the 6th.
It's just how many zeros are.
Yeah. Or how many decimal places.
And
to
yeah,
go with.
what will you make us do with that?
So maybe I say that, you know, 1 eggplant is 7 million orangutans.
That's a lot.
Why?
Because
you
apparently
can't.
eggplants are incredibly valuable, or the value of the
So
orangutan
you'd
has
say 7
plummeted.
to the 10, 7 times 10 to the 6.
Orangutans for
Eggplant?
eggplants. I guess in that example, yes.
Okay, so you won't, or no, another question. So when you just say 7 million, so do I need to know how many zeros are in a million?
No, I would tell you the proper numbers.
So you would like write them
But the
out?
question is, I might write them in scientific notation.
We have to then say what it was. Like,
I mean, you have to be able to use that in a calculator.
we have to say like, oh, it's 7
Oh,
million,
that's
or we
not
just
upright.
put 7.
Yeah, you have to give, like, you have to put in a calculator. A calculator will probably spit out something in scientific notation. Like, you have to be able to understand scientific notation, because when you put a lot of times these numbers into a calculator, it's going to spit something out in scientific notation. So you really need to be able to deal with it. Is basically the point. I don't need this translated back into English, but I need you to be able to figure out if you're getting something that's reasonable or not.
So first period.
Okay. We will pause here. We will resume with the back half and any questions tomorrow.
Pausing.
These are the hard clips, I think.
Conversions
Thank you very
and
much.
optics. Okay.